Welcome to the Quantum Feedback Loop podcast. I'm your host, James Myers, and I also publish the Quantum Record, which features the latest in science and technology. This June, the Quantum Record reported on the successful creation of a new physical object called a time crystal that oscillates between two states for as long as 40 minutes without any external power source. The idea for this new phase of matter was conceived only a dozen years ago by Nobel laureate Frank Wilczek, but now time crystals are quickly moving from theory to practical application, and so we were pleased and honored to sit down with Federico Carollo to find out more about what time crystals do, how they operate, the current state of the science, and what discoveries time crystals could lead to by giving us a new platform to probe physics. Federico is a postdoctoral researcher in theoretical physics at the University of Tübingen in Germany, and his recent work focuses on possible applications of time crystals for sensing and estimating external parameters like magnetic fields. It was fascinating to explore with Federico what time crystals tell us about thermodynamics, the consequences of breaking time translation symmetry, and the potential uses and technologies that could emerge with this new dynamic phase of matter. While time crystals don't promise to be perpetual motion machines, I hope you'll come away from this talk as excited as I am to think about the potential for a future with time crystal technology. Welcome, Federico, to the Quantum Feedback Loop podcast. I'm really interested in learning about your work and more about time crystals.
Thank you very much, James, for inviting me, actually.
Well, it's great to have you. And maybe you could start by telling us a little bit about your background, what you're researching now.
Yes, sure. So I actually have a rather mixed or probably peculiar background for a physicist, because actually I have a bachelor and a master degree in naval architecture and marine engineering. And only after getting those, I actually switched to physics. And I had a PhD in theoretical, almost mathematical physics, I would say, essentially dealing with emergent structure and emergent dynamics in many-body quantum systems. During the years then, during my postdoc experience, I've worked on several aspects of quantum and classical non-equilibrium, both, let's say, on a more technical side, like developing tools like mathematically rigorous results on many-body systems, as well as developing numerical approaches to simulate these challenging quantum systems on classical computers. I've also, of course, worked more on a fundamental side, closely related to the topic of today, by studying non-equilibrium phases of matter and phase transitions, open quantum dissipative dynamics and quantum thermodynamics, and so on. I have a lot of collaborators, and actually, currently I'm working on many of these topics with probably particular attention on systems with long-range interactions, so system whose microscopic constituents interact even if they're very far apart, one from the other, stochastic dynamics, as well as quantum versions of neural networks. So this is somehow my playground, if you want.
Very, very far-ranging, actually. Yeah. And so maybe we can talk a little bit later on about the connections to information in terms of thermodynamics. I understand there's a connection. So maybe at some point we can get into that. But I wanted to talk about the start of the idea of time crystals. So time crystals were first theorized a dozen years ago by Nobel Prize winning physicist Frank Wilczek. And for listeners who haven't heard the term time crystal before, or who have but aren't sure what it is, can you give us a general overview and how this connects with many body systems, I think, that you were talking about in your research? And I guess, first of all, these aren't crystals that are like diamonds or other physical objects that the average person would know. Is that correct?
Yeah, indeed. So these are not like diamonds or other crystals, but they're very much inspired by them, and they owe their name to these objects. So very generally speaking, let's start maybe saying what is a crystal. So a crystal is a solid material whose fundamental units, which could be atoms or molecules, are arranged in an ordered structure which repeats itself in space. So you can maybe imagine a mosaic whose tiles form a pattern which repeats in one, two, or many dimensions. Okay. Of course, this has a sort of sense of triviality. So to make this a bit less trivial, what we have to add is that this periodic structure in space should not come by some external arrangement, but it should really be a sort of collective effect of a many-body system. So some self-organization behavior which is emerging in a system composed by many interacting units in a particular state, in some fundamental state. Typically, we look at this in ground states or thermal states. Okay, so this is somehow what crystals are. So now we know, in some sense, since the work of Einstein, if you want, that time is just another dimension like space, like the spatial one. So the idea of Wilczek in this seminal paper was to explore and try to understand whether it could be possible to have a crystalline structure in time. So now what do I mean by this? I mean a system that repeats periodically, but now not in space, but in time. Okay, so you can imagine a pendulum maybe, which is oscillating and in coming back into its previous position only after some period. Of course, to make this interesting, a pendulum, okay, so interesting is the workhorse of physics, but it's not a time crystal. So you should imagine again that this periodicity in time should emerge again as a self-organization, as a synchronization of many interacting units, and should not be a single particle effect like what we would define that of a pendulum, nor this oscillation should be forced or externally imposed by some periodic driving. So spontaneously, a piece of matter should start oscillating in some fundamental state in time.
That's really helpful, actually. And when you say pendulum, it makes me think, I guess, going back to Galileo's famous experiment in the cathedral in Florence, I guess it was, right? Or was it Pisa? Where it was just the idea of looking at maybe two limits. You know, you start the pendulum swinging and it swings from one limit to the other limit. And so as time crystals, is it the idea of creating maybe these two limits that these quantum states are oscillating between?
This depends on the type of time crystals we are talking about. There's also a flavor of that, if you want, in certain types of time crystal. Yes, if you think of a discrete time crystal, this would be something that would oscillate in between two phases, between two states. But in general, from the previous definition that I gave, it's really something that shows oscillations in particular out of some static driving. So some law of motion which are time independent.
And it's localized in a particular time frame or spatial frame, I guess, where it doesn't become universal. It's localized in a specific state. Do I have the idea of localization correct there?
Well, localization is something that played a big role, like many-body localization, in realizing this discrete time crystal. But if you have in mind the original idea of Wilczek, I'm not sure. Of course, in crystal, you have a flavor that something is localized, and maybe if you have a crystal that is starting rotating, so this motion of localized object could also generate a time crystal. But I don't think localization is an essential object.
Okay, well, maybe let's go to the idea of symmetries. And so it's said that a crystal, like a diamond, breaks spatial symmetry. And I'm just wondering how you explain symmetries like space translation symmetry and time translation symmetry, and how these would operate in a time crystal. I understand a time crystal would break time translation symmetry.
Yeah. Yes, indeed. So this is indeed important. I mean, it's somehow the definition of a time crystal is something that breaks time translation symmetry. And similarly, also a crystal is something that, as you said, breaks the spatial translation symmetry. So let's start with symmetries, as you said, and let's maybe try to have a simple example in mind. So imagine to draw a circle on a piece of paper and to look at it, right? And now you apply a rotation. So you rotate the circle around its center. Now all points of the circle are moving, but what you see is exactly the same object. This is the sense of symmetry that we have in geometry or physics. So what is a symmetry? It's a transformation, if you want, that leaves a system or something that belongs to the system invariant. If you come to the example of the circle again, so you rotate the circle and any angle that you apply, you always get the same shape. This is a continuous symmetry because any angle I apply always gives me back the same object. This is not the same if you have a square. If you draw a square and you rotate it, what you see is different if you rotate it around the center. It will only be equal to itself if you rotate it by 90 degrees. So if you specifically hit angles which are multiples of 90 degrees, you get the same form back. This is still a symmetry, but now it's discrete because I'm only allowed for certain values. It's not continuous rotation that leaves the object invariant, but it's precise values of this rotation, if you want. So symmetry, transformation that leaves the system invariant, and we can have continuous symmetry and discrete symmetries. Let's go back to crystal. So crystal is a physical system, at least we describe it as a physical system. And there's a very important operator or function in physics associated to any physical system, which is the so-called Hamiltonian, which is the energy operator. So it contains or describes, encodes the energy of the system. It can include kinetic energy, so energy due to motion, or interaction energy between different particles, and so on and so forth. So typically, these energy functions are invariant under spatial translation. So if I move my system, the energy, I describe it in the same way, with the same functional form, if you want. This is somehow related, I guess, to the thought that the laws of physics are the same everywhere in space, right? So now we have a system, an Hamiltonian, an energy, which is symmetric under spatial translations. What we typically expect is that the state of the system, a fundamental state of the system, like the ground state, which is the state I can now start defining things with lowest energy of the system, or a thermal state, which describes the system in some thermal equilibrium with an environment. What I typically expect is that this is symmetric under the same symmetry of the Hamiltonian. This is, let's say, a trivial phase, if you want. To make things a bit concrete, let's say maybe we can take a one-dimensional system. So we think we have a line, particles on a line that interact with some energy, which only depend on the distance. Can be some attractive potential, which only accounts for how far the particles are. So now, if this is the energy, if I shift the system, I also shift solidly all particles, so the energy is always the same, is invariant under spatial translation. And now a state, for instance, that is also invariant under spatial translation could be, I don't know, some liquid in this one-dimensional system. It uniformly occupies my system. So if I move my reference frame, if you want, if I shift space, I see always the same state. Okay, so this is symmetric Hamiltonian, symmetric energy function, symmetric state. No symmetry breaking here. What can happen is that due to a variation of some control parameter, being temperature, being a parameter in the energy, being whatever, what can happen is that actually my system forms a crystal. So now it is not uniformly spread in space, but it forms a periodic structures with some, let's say, indeed, a periodic structure which originates from somewhere, from one particle in some points, and develops in both directions indefinitely, right? So now the system has chosen a precise configuration starting at a given point in space. If I move space, my system is changing now. The state of the system is changing. Unless, of course, I don't hit exactly the spacing between particles. And if I move my system by exactly the spacing between particles, I get back the same. So we have an energy which is invariant under any possible space translation, but the system is only invariant if I move by a given spacing. So my state is less symmetric than the energy function, and I have a symmetry breaking in this case. That's how crystals are said to break spatial symmetry, because they select a precise configuration and a precise starting point, if you want.
That's really interesting. And that I found the way you described it with a circle was really helpful to bring the image to mind in terms of the symmetry being complete. Wherever you are in the circle, everything looks the same. Whereas with the symmetry breaking, you have this repeating pattern. So instead of getting this continuous development, I guess time translation symmetry, I think of it as maybe the idea that a broken glass doesn't reassemble itself, or a broken egg doesn't unscramble itself. And so in this repeating structure, though, where you've broken that symmetry, you do have that going back and forth to those different states, right? Like you'd have a broken glass going to a fixed glass, going to a broken glass, going to a fixed glass. Is that maybe an image in mind? Would that work?
I'm not sure. No, I think you really have these two states in mind, which are strongly associated with this discrete time crystal. But in principle, if you think that you break time translation symmetry in a continuous manner, what you simply would observe is some limit cycle. Okay. So a state which approaches some oscillations. Of course, this involves more than two states. Oscillation, in particular for a quantum system, involves an infinite number of states, if you want.
Okay.
Maybe I can try now to translate this story for crystals into time crystals, because this is really analogous. let's consider a system now whose equation of motions. So before we spoke about this energy function, now let me introduce this equation of motion. For instance, for isolated system, these are still encoded in the energy function. So, but let me assume we have a system which is described by this equation of motion, which are the laws that govern the dynamics. And these are invariant under translation in time. So if I look at different times, the equation of motions are the same. This is again underlies a principle that if I do an experiment today or tomorrow, I see the same physics. Or in 100 years, I will see the same physics. Okay, so physics should be reproducible. And we kind of rely with this on the time translation invariance of the law of motion. Okay, and now we have these laws of motion, which are time translation invariant. So if I shift time, this doesn't change. And now let's take some fundamental state, for instance, again, the ground state of a system. So if the ground state is now time translation invariance, meaning it doesn't depend on time in this case, what I have is a ground state, which is the fundamental state of a system, which obeys the same symmetry of this equation of motion. But if this ground state starts to oscillate, this was the idea of Wilczek, would show some limit cycle dynamics, for instance, then what I would have is that the state repeats itself only periodically. So only if I wait a period, the state comes back to itself. And while the laws of motion, they are continuously symmetric. So any shift in time would be fine. So again, I would have a state which is less symmetric than the equation of motion. This is somehow the idea of time crystal. The rules of the game are time invariant, but my states spontaneously start to oscillate. This is continuous time crystal.
Okay, and invariant meaning that it doesn't change over time.
Invariant means, sorry, yes, that it doesn't change over time.
Doesn't change over time, okay.
Yes.
Okay, and that's really helpful. So I think you've mentioned the word equilibrium, and you talked about those points on the line sort of equalizing over space and time. And I'm just wondering if you could talk a little bit about time crystals and how I think you've said that they aren't possible in an equilibrium state. And so maybe if you could just explain a little bit about equilibrium and how we should think about equilibrium, maybe in the context of thermodynamics. And, perhaps in the sense that most people would likely be familiar with thermodynamics. Like, for example, when we see that cold objects don't spontaneously become hot and that over time energy spreads out equally in space. Is there a way that you can talk about equilibrium as it relates to time crystals?
Yes, I think so. And actually, I think this is really the notion of equilibrium we should have in this setting. This is not only for time crystal. When we talk about equilibrium in physics, we really mean, in some sense, thermodynamic equilibrium. So let me maybe elaborate a bit with some simple example. So imagine you have, again, some system, some piece of matter that you put in an environment. This could be a room, a refrigerator, or some oven even, at a given fixed temperature. So you put this object into the room or into the oven. What you would expect is that initially you put this system here, it feels a different temperature from its temperature. And what starts there is an exchange of energy between the system and the environment. So in the form of heat, there will be some transient in which energy is exchanged. With time, though, the system would somehow relax or equilibrate at the same temperature of the environment in which I've put it in. So it arrives at a situation in which we would say is in thermal equilibrium with the environment, with the rest. And here, any exchange of energy would stop. So in this equilibrium condition, there is no net flow of energy or of matter between the system and the environment, and no net flow also between different components of a system, if you want. So in this condition, we say the system is in thermal equilibrium, and it's typically described by a thermal state, so-called thermal state, or the ground state if the system is at very low temperature, like this absolute zero temperature, okay? So, and now in connection with time crystals, what I would say is that there is now some general agreement that in this condition, in this equilibrium condition, time crystals are not possible. So looking at this from the opposite perspective, in essence, it seems that to have a time crystal, it is fundamental to have a constant energy exchange between the system and the environment, and maybe we should also have some energy source for the system. Or what we could have also is somehow we would have to come up with some mechanism which would try to avoid the thermalization of the system and would keep it out of equilibrium with its environment. This is where many body localization play the role in the realization of this discrete time crystal. It is a mechanism which would somehow prevent the system to absorb energy and to thermalize to, let's say, some infinite temperature state or some high temperature state.
So the net flow that you're talking about would be between the system and the outside environment, and in equilibrium, there would be no net flow either way from the system to the environment, or yeah, okay. Okay, and so you're saying that that would be one idea, is to create a system with no net flow, or another system that would retain its own flow, I guess.
When we are really in equilibrium, there's no flow inside the system, in principle, no net flow. I'm not saying that on average, nothing moves, but of course you can have fluctuations of flows. The point is that if you manage to be in a non-thermal state, so if you avoid arriving at thermalization, you can do this several ways. Like one is to put some energy source on the system, which keeps it at a different temperature from the environment, let's say. Or in principle, you should really try to avoid thermalization. So somehow making the system not able to absorb heat from the oven in some sense.
And is that the difference between the discrete time crystal and one that's continuous?
Okay, good. This allows me maybe to explain a bit better. So the distinction is now simply related to what kind of time translation symmetry they break. So remember when I talk about symmetry, I do this on purpose. I actually presented a continuous symmetry and a discrete symmetry. So a discrete time crystal is a phase of matter in which the state breaks the discrete time translation symmetry of the law of motion. A continuous time crystal will be a system, so a phase of matter, which breaks the continuous time translation symmetry of the law of motion. So let me make it maybe a simple example. So imagine that you have some law of motion, which, because of some driving from the exterior of the system, depends on time periodically. So you have some equation of motion, which at every period, they are equal to themselves only if I shift time by a given precise period. So what you would expect under these conditions is that after long times, for instance, or some fundamental state of the system, would also present oscillations which have the same period of the equation of motion. So I'm driving the system, forcing a period. I typically expect my system to show the same period. What can happen, however, and this is one of the first experiments, I think, for time crystal, they were showing this discrete time crystal. What can happen actually is, however, that the system, for certain parameters or for certain conditions, starts to reply by showing a state that actually has a periodicity which is a multiple of the period of the equation of motion. So a multiple of the fundamental period. For instance, twice the fundamental period. And so now you have a state which is equal to itself only after 2 periods, while the equation of motion are equal to themselves after 1 period. So there is a discrete time translation symmetry of the generator of the dynamics, so this equation of motion, that has been broken by the state. This is more the notion of discrete time crystal that maybe you have with system oscillating between 2 states and coming back to itself only after 2 periods. This is probably the picture which is closest to this idea that you were mentioning before. In a continuous time crystal, instead, what we have are laws of motion which are time independent. They do not depend on time. So every shift that I do, they give me back the same equation of motion. The generator is really time independent. But now the state of the system, for some reason, starts to show oscillations out of this static driving. So it autonomously pick a frequency which depends from some parameter and start to oscillate with that, even if the driving is completely oblivious of any frequency there in some sense. Does this make sense?
Yeah, interesting. So the discrete kind of creates a multiplier of the input, I guess?
Response, we say somehow. So responses, yes, which are multiples of the driving period. So
okay, yeah, really interesting. So in terms of the key thing that a time crystal could accomplish? I mean, I guess when Wilczek thought of it a dozen years ago, what was the outcome he was thinking about? What would be the major, if we could develop these things to operate with no limits, what would be the key thing that it would produce for us?
This is an interesting question. I'm not sure I can really fully reply to it, but I'll try to give you my perspective, which is a very fundamental and at the moment academic one. But the point is, I think what Wilczek wanted to prove, in a sense, to accomplish, to achieve, was simply that the time symmetry could be broken. So he was devising this time crystal just to make a point that time is really like any other dimension, and we can even break the symmetry which is associated with time translation. Now, we said maybe Wilczek's idea was in equilibrium, so maybe this is not really possible. It's debated. There had been several discussions immediately after Wilczek's paper. But what is certain is that we can achieve this, we can accomplish this, we can break time translation symmetry in out of equilibrium conditions. And I think this is a very big accomplishment, so achievement. If you think about it, I mean, time crystal constitute, if not the first, a very paradigmatic example of a non-equilibrium dynamical phase of a many-body system. So typically when we talk about phases, liquid, vapor, solid, I mean, these are all equilibrium phases. So meaning really in the framework that I told you 10 minutes ago. In a thermal equilibrium, we have these phases. We also have a few non-equilibrium phases, which are continuously discovered. Of course, there is a lot of interest now also in non-equilibrium systems. And but I think this is really one of the first, or maybe the first, which is showing a continuous dynamics, which is emergent from self-organization. So I think this is very interesting, and this is already something that has been accomplished by time crystals. So they provide an example or a platform in which we have this very interesting non-equilibrium phase, and which we may use both to, I don't know, probe new physics and maybe think of new applications. This is really something new, I would say. This is what has been accomplished, in my opinion, by time crystals.
Really interesting. And so, yeah, you mentioned the phase change, from water to freezing, liquid to freezing, for example, liquid ice. So does the idea of a time crystal, if we can produce that, are you saying that it would allow us to maybe measure phase changes in physical matter in the sense of like what's going on exactly at the moment that there's a phase change?
Well, this is certainly not what I was saying, but
Yeah,
it's an interesting thought. Yeah, this may be possible. Yeah, I know. Yeah, what is somehow also known is that this could be, at least at theoretical level, this time crystal could really provide some very good sensor, so they could sense some parameter which may cause a phase, or maybe, yeah, also for timekeeping in a sense. So yeah, there's a few, of course, there are a few also practical application that one could think of time crystals. But I think the biggest achievement is what I told you. I mean, they really provide a new platform to probe physics, or even new mathematical structure, if you want, is interesting from a very broad perspective.
And I was actually, when I was saying that, I guess I was thinking of the sensing potential for it, which maybe we can talk about in a little bit. So I've heard reference to time crystals in the context of perpetual motion machines. Is there any connection that we can make to that in the sense that it's this continuing oscillation between phases that doesn't consume any external energy, I guess? The ideal time crystal wouldn't cause energy to be gained or lost. And so theoretically, could it continue forever, theoretically?
So we're jumping again into this equilibrium framework. And yeah, this point of time crystal being close to perpetual motion machines, I mean, have been raised immediately by Wilczek himself somehow in his seminal paper. I don't think they are perpetual motion machines. And I also think that this is good. And when I say this, so luckily they are not perpetual motion machines, I say this because I have in mind a quote by Eddington, so a physicist who's studying also special relativity, was another physicist. But essentially, this quote is very funny, in my opinion, but it really gives the sense of how important is this second law, which is something that somehow would be violated, if you want, by these perpetual motion machines. It was saying, like, if you have a theory, I mean, this theory can be against any other theory or well-established concept in physics. Like, your theory is against Maxwell equations, I don't care, that's fine. But if it doesn't comply with the second law of thermodynamics, then, I mean, it's a game over. Your theory is done. No one would take it seriously. And I think this is the same for time crystals. So luckily, they're not perpetual motion machines because no one would take them seriously if they were. And clearly, one would be tempted, I think, to think that there's something funny going on because I have these oscillations that go on forever. And I think to try to rationalize this, let's keep again the example of Wilczek that he has. So he says, we have a system, we are in the ground state, and this ground state essentially starts to oscillate. This is more or less the Wilczek time crystal, okay? For the moment, let's assume this could be possible. I don't want to enter the debate. So we have a ground state, which is in equilibrium. So if you remember what I told you before, there is no heat flow between the system and the environment, let's say. So there's no heat flow. And also this state is a ground state. So it's a very precise and ordered, we would say, state, which would oscillate, but it would still be a so-called pure state, which is oscillating. So we have perfect knowledge of this state. And in this sense, there's no violation of the second law, because the second law essentially is telling us that order cannot increase, but it still allows to be the same of before. Okay, so this marginally satisfies the second law. Also, there's some motion in there, coming back to try to rationalize this. So there's some motion, but we are always in the ground state. So the energy is fixed. This would be somehow, I've also read in some papers or in some references, this would be somehow motion without energy. So it's not really, there's no possibility of extracting this energy. So this would not really be a problem, I would say, with being too close to perpetual motion machines.
That's a great explanation, I think. Yeah,
okay.
it really, yeah, so the idea that under the second law of thermodynamics, order can be the same but not increase. I think that's one of the key ideas. So this is keeping the same order.
Yes, in this equilibrium setting, it would keep the same order.
Right, and not being able to extract the energy, which is, I guess, those who would like to develop a perpetual motion machine would obviously want to be able to extract the energy so they could do something with it.
Yes.
Okay, so yeah, so interesting. So we're creating this oscillating ground state, I guess, is what you're saying.
Yes, let me only add that for the time being, it seems that this is not possible in equilibrium. So we could create something that oscillates for sure in non-equilibrium conditions, but there are some sort of boundaries or no-go theorems, as we call it in physics or mathematics, that are telling us that very likely this is not possible in equilibrium.
And so I guess when I mentioned localization earlier, I guess I had a picture in my mind of this oscillation just being for this particular configuration that doesn't extend beyond its own limits. It has its own limits and it doesn't extend beyond its limits. This
phenomenon of localization is somehow, you can imagine you have again a one-dimensional crystal, if you want. Essentially, this localization happens typically when you have a disordered crystal. So for instance, when the on-site potential of these different lattices in the crystal are different and there's some excitation that could hop in between them, but okay, they are different. And what happens in this case is that this excitation localizes. So if you put it in a place, it would remain there. While in a perfect crystal, it would go everywhere. In a localized system, it would stay put where you put it.
Okay, that gives me the picture. I think that's helpful. So in terms of the work that's been done so far in developing time crystals, in the quantum record, we reported recently on a group of researchers who created a crystal that could maintain its oscillations between, I guess, two states for up to 40 minutes.
That's actually a continuous time crystal, I think. This paper, I guess, I think I've seen your quantum record report on this Technical University Dortmund. I think that's a continuous time crystal. So it's one of these examples in which they were able to apply some time-independent law of motions on the system and to get some oscillations out of it. There were energy flows there because they were driving somehow the system, at least this is what I got from the paper by reading it, to counteract these energy losses due to dissipation. And with that, they could engineer a system that shows oscillations for, I mean, forever, essentially. Right. If we think in physics timescales, this is really quantum physics timescale, this is ever. Yeah.
And initially, I understand there was a type of time crystal called a Floquet time crystal, I think. And that's where, as I understand it, energy had to be added periodically to it to keep the oscillations going. Is that correct?
Floquet time crystal is exactly the discrete time crystal. We use this word in physics, so Floquet driving or Floquet system now is something that is periodically driven. So you should imagine like that. Floquet means periodically driven. So this is exactly, a Floquet time crystal is a discrete time crystal.
And then so the group in Dortmund was creating a continuous one that would operate without the addition of external energy for 40 minutes, I think is what they reported.
But I think it's important, they were driving the system. So they had some optical pumping on the system to replace excitation due to losses. So there's some energy intake.
Yeah, interesting. So if they were to be able to extend that, from 40 minutes to 40 days or 40 years, what sorts of things do you think could follow from that? What sorts of developments do you think could flow from that?
Well, yeah, it's a good question. I never thought in these terms, but I guess what comes to mind is some clock, maybe, some very precise clock, which could actually, contrary to, I would say, the clock that we have in mind, pendulum or whatever, or even this atomic clock somehow, it would rely on some self-organization, so some collective behavior of the system which spontaneously organize itself in some oscillation. So I think this could provide, everything needs to be shown, so it's just somehow speculation if you want here, but what could provide is somehow very precise clocks. You have these periodic oscillations, which are a collective effect, so this could result in some sense on very sharp and robust ticks of the clock in some sense.
And I guess it's because maybe it's not exchanging energy, it's not losing energy to the external environment that it would be able to make these accurate measurements. Whereas maybe a regular clock, if we think of it ticking around, it's losing a little bit of energy every time it ticks around, right?
Well, but here we have also to understand that if we want to use these systems as clocks or in whatever technological way, I think we would have to measure at some point. So this is probably a subtle point, I think, subtle point for quantum technologies in a sense. We always have this thing that we would have to be able to measure and to measure proper quantities.
And I guess there's always that observer effect problem of measurement, I guess, in quantum. When you look at it, you change something about it.
Yes. This is the problem with quantum systems. Like if we perform a measurement, we destroy the state of the system. So we collapse it into the outcome of the measurement. This is indeed a problem. I mean, can be overcome. There are now these sort of weak measurements, in a sense, which we can imagine. We don't completely perform a measurement on a system, but we look, for instance, at its interaction with the environment. So we look at the photons that are emitted. This gives us some information on the system. So it modifies the state, but it doesn't really completely destroy it, if you want. So there are ways, but this is exactly what we need to understand in order to be able to use quantum systems.
Is maybe the idea of measuring the probabilities or the relationships between probabilities in the system, instead of measuring the system itself, but measuring its characteristics and probability? Is that maybe a form of measurement?
The point is that experimentally, you cannot really measure the probability. You can repeat experiments and get probabilities that you can do. But of course, you would have to run your system, measure reinitialize your system, run the same dynamics measure, if you understand what I mean, because destroying the state of the system means that you always have to re-prepare it after each measurement. So what I'm actually saying is more like I do not measure the system. So I do not measure a property of the system, but I measure the property of some interaction of the system with something else. So I couple the system with some ancillary degrees of freedom, and then I measure these other degrees of freedom. So I try to keep the most. Essentially, this is what is called a weak measurement. I try to do not spoil too much the system. This is what they do in experiment, for instance, when they look at photons that are emitted and so on and so forth. This is only one of the few measurements that we can do. We cannot do whatever we want with quantum systems.
Interesting. And does your work involve any experimentation, or are you more on the theoretical side?
I'm more on the theoretical side, and what I also like. So I try to keep an eye on what's also possible with experiments, and always have this try to connect with experiments. I'm mostly theoretical.
I'm wondering too about thermodynamics itself, the whole process. So I think some of your research looks at specific aspects of fluctuations, I guess, is what I'm thinking of. And when I think of thermodynamics, I guess I'm thinking in a sense of, the probabilities I mentioned just a minute ago, in terms of, as you described it, where you start off with the lowest number of probabilities, I guess, under the second law of thermodynamics, and then it ends up in the highest number of probabilities, like the disorder increases over time. Is that probabilities increase over time as a result? And is there any sort of thing either with that or anything else in terms of thermodynamics that we might discover in pursuing time crystals?
Yeah. So coming to the first question, somehow we have the second law, which, let's say, at a fluctuating level, so by single realization, for instance, if you think of a stochastic dynamics, this could be violated. So there are somehow probabilities associated with certain events that may violate the second law, but the point is that on average, so when I integrate overall probabilities, let's say, this cannot be violated. This is the second law of thermodynamics, in the sense that it's very important that it's not violated. And coming to the other question, so what can we maybe learn about these aspects, these thermodynamics aspects with time crystals? I'm not sure. What I think is the following. And this is somehow also related probably to the work that you are mentioning of mine. There's a key challenge at the moment that time crystals are just thrown into the face of everyone. At least this is my viewpoint, with there being paradigmatic non-equilibrium phases. So what we still do not fully understand from a quantum thermodynamics viewpoint is how to have a general thermodynamics understanding and descriptions for quantum systems that are genuinely out of equilibrium. Okay, so we discussed about equilibrium before. So we know how to describe dynamically this process of thermalization, and also thermodynamically, and everything is fine there. We also know how to consider and to describe dynamically and thermodynamically systems which are coupled with different environments which keep them out of equilibrium. And so in this kind of non-equilibrium situation, okay, what are we still missing? At least there's a sort of general agreement that what is still missing is some systematic understanding of this quantum system, which are in contact with some external environment, but they are also driven by some coherent energy source, like the laser we were discussing before. So more generally, we lack a full thermodynamic description, I think, for systems which are in contact with environments, or at least a general thermodynamic description for systems which are in contact with environments that do not, singularly taken, leads to thermalization. And this is a key problem from my perspective, because these are exactly the systems that we are producing experiments. So I think that all these interests in time crystal, their behavior, they may look close to perpetual motion machines. So this makes me curious. Let's have a look. And the fact that we can observe these phases in experiment, they are there. Hopefully, they will motivate also some research on this aspect of quantum thermodynamics, of these driven dissipative systems. Something has already been done. Also, as you mentioned, some of my work, but also, of course, many people are working on that. And with a few collaborators, we have tried to give a picture or couple of thermodynamic picture of this possibility. also having in mind time crystals. But there's still work to be done, definitely. And in a sense, being a bit provocative, I mean, the challenge that we have now, we have these systems that are producing experiment and which we do not fully are able to describe that thermodynamically. And maybe this is where all this attention in time crystal could play a role for thermodynamics, I think.
Mm.
At least this is my hope. This is what I'm interested in.
Yeah, I mean, that would be fascinating. I mean, as you said, I guess the idea of creating a general description of systems out of equilibrium, I guess, if I have that right, is the idea of being able to say like these out of equilibrium systems could be each different, but to create some sort of general rule that would apply to them all.
That's the hope always, right?
Right.
Going to in physics, or what we like to do is to go from a specific results and to make it somehow as general as possible.
Interesting. Now, I've heard discussion, and I think it may have been the Dortmund group as well, that was talking about the potential of time crystals maybe to help in quantum computing in the sense of dealing with the error correction problem that exists there, which arises because of the interaction of the qubits with the external influences like, thermodynamics, electromagnetism, and all of that. So I don't know, have you heard much discussion about any potential relationship to quantum computing and time crystals?
Not really, honestly. So I'm not really aware of this potential, let's say, of time crystal with quantum computing, but I'm sure they may have potential there. Yeah.
So in terms of your own research, what's the most exciting thing upcoming, do you think, in what you're focusing on?
So, for instance, we are also working, we have a few works which we are also pursuing and keeping this in mind, really with time crystals and possible use of these as sensors for sensing external parameters like magnetic fields and so on. And I think they have some great potential also for this aspect. So they can be used for parameter estimation or sensing. And again, what we would like to exploit here is really these collective effects that are associated with this time translation symmetry breaking, together with the fact that according to a very small variation of some parameter, this system can pass from a time invariant state to one that shows oscillation. So there's a macroscopic change that it's happening out of a very tiny, let's say, variation of some parameters. This gives increased sensitivity to parameters, which may be used for estimation. Of course, there's a challenge somehow. What I was telling you before, there's a challenge because we can, for instance, measure the potential of this system for sensing by means of information theoretic quantities like Fisher information and so on that would tell us, yes, the state of your system has a lot of information about the parameter that you want to estimate. And in theory, this is beautiful. But the point is, if you think in terms of quantum technologies, the point is, okay, in theory is beautiful. I have a lot of information in my state, but these quantities typically do not tell you what do you have to do to extract this information. And maybe you should also talk to the experimentalist, what I was telling you before, to try to understand what can you actually do with this system, what can you measure, because they will not be able to measure everything. So I think the key point here, if we want to go towards technologies, is really to try to understand from a theory side, what are the nicest protocol that we could do to extract information for sensing, for instance, or for clocks, or we brought this out for clocks, but this applies also for the case of sensing. We would like to find protocols for which we can get information from the system, which, however, should match what is possible in experiments. So that's why I told you before I'm a theorist, but I like to keep an eye on what's also possible in experiments, because if we want to arrive at technology far away, very far away, I think, of some form, this is what we have to do.
And so if there was a particular sensing, or maybe more broadly, a listener might think of measurement technology, is there a specific application that you have in mind that might arise from your work?
I think there's a lot of interest in, for instance, sensing magnetic fields. And it happens that in certain models of time crystals, the control parameter which makes the transition happen as a flavor of a magnetic field. So this is probably what would be.
Well, I mentioned, I guess, at the beginning, the potential connection to information theory. And so you've just mentioned information, I guess, and the idea of how to extract information. And so I guess to the extent that these create a greater amount of information that we can access.
The idea is that, let's say, we have these information quantities, like for the expert, what I was referring to is this Fisher information. I don't know, maybe I already mentioned it, which is telling us that, for instance, with time crystal, we could sense parameters, estimate parameters better than with classical devices with same amount of resources. So one has always have to have a fair rule of the game. And these quantities shows, for instance, scaling with the time of the observation and with the number of particles. These are both resources, time of observation and number of particles. And what you can see is somehow that, for instance, these quantum systems seem to behave better as a scaling with the number of particles than classical ones. In particular, these time crystals in this case.
Scaling, and I'm thinking the idea of multiplying the information that we can get. So we can,
in a sense, yes.
Yeah,
yes.
So we apply the same resources to get information, but we can do more with
more
that information.
Yes. It is something that does not only happen with time crystals, but it happens when we have quantum correlations. So when we have this quantum correlation, this entanglement, it can be, right, that we are able to sense, so to estimate a parameter with a smaller error, with same amount of resource. This is only due to the presence of quantum correlations.
I guess that's what made me think of probabilities earlier, to the extent that I guess I think of Heisenberg's uncertainty principle. We can never have absolute knowledge of anything, but at the end, I guess we're kind of narrowing down the probabilities that we can measure. Does that make any sense?
This is probably the case, yes. Typically, the parameter that you want to sense is, however, let's say, an external magnetic field or something that you would describe classically. So Heisenberg principle is not there hunting you, let's say. So you could diminish the variance, because the Heisenberg uncertainty principle is a statement about variances of quantities or quantum operators. And also these quantities that I was telling you before would tell you that you can decrease the variance of some estimate objects, so the error, by increasing the number of particles. And according to how this behaves, it can scale faster or slower with the number of particles. So you have a gain if the error goes down faster with the number of particles rather than slower. Then I'm really thinking about inverse power series of 1/n.
Yeah, and it's fascinating to think of how much we could do with this, I guess. Thank you very much for your time in this. I learned a lot from the discussion. Maybe if we can move to conclude in terms of what you think the next major step would be in time crystal development, like developing this technology and developing its applications, where we are now, whether it's the Dortmund group maybe has the best time crystal example, or maybe others do. What would be the next step, do you think, the next major step that would take us to the next level of potential where all sorts of different ideas start to emerge?
I think this is really now, we should start to realize that there's much interest here. Everything started with this paper by Wilczek, the condition of the possibility or the debate whether we can have or not time crystals in equilibrium or not. And this debate triggered a lot of interest and a race to realize time crystal and to understand in which condition. And then we had experiments, a lot of experiments like Dortmund group. There are other experiments which show that we can essentially create time crystal at room temperature without sophisticated fine-tuning and so on. So what I think is now the next step, since also from the theory, we are understanding that these objects are good, possibly good for technologies like sensing or timekeeping or whatever. We really need to start, I think, to get together people from quantum information, people from open quantum system and dissipative dynamics and non-equilibrium statistical physics, and experimentalists, try to understand what can be done with all the constraints that all these different groups of researchers have to go towards the technology. So try to, as I said before, develop algorithms that exploit time crystal, but that are realistic from the eye of an experimentalist. This is where we should now aim, in my opinion. And of course, I mean, we're probably not too far away from proof of principle application of time crystal technologies. But okay, we should always try to understand what the next step is. We should be to bring that technology out of physics laboratories. And that's also a big open question.
So there's a lot of people like yourself, I guess, now working on the theory, but I think what you're saying is that we need to gather the theorists, the experimentalists, and the people who would actually be using the technology together to blend all of those ideas and to drive some more ideas out of it.
Also require bringing people from industry if one really wants to go to technology, because when I say, okay, you can realize time crystal without too much fine tuning, but this is still done in a physics laboratory. It's not in a, I don't know, with a phone, for instance, right? So this is the next real challenge if you want to use this technology.
Well, that's great. I think that's the benefit of conversations like this. You know, the more people that know about it, the more ideas can start to flow about it. So yeah, I really want to thank you for your time. I've learned a lot from this discussion, and we hope to see more of your work and see the next steps evolve. So I want to thank you very much, Federico, for making the time for this.
Thank you, James. Very interesting experience, I have to say. It was a very nice discussion, and thanks a lot for allowing me to talk also a bit about what my interests are.
Thank you so much. Our thanks go to today's guest and to you for listening to the Quantum Feedback Loop. Please subscribe to this podcast wherever you get your podcasts, and don't forget to check out the Quantum Record at thequantumrecord.com. The Quantum Record is a monthly journal of philosophy, science, technology, and time, where you'll find the latest developments in our rapidly evolving technological world.